Okay, good morning everyone and welcome to your week 6 math lecture for dynamics. I thought I would have had a full class for once, but half of them just left unfortunately. So last week you should remember we looked at the topic of free vibration. We showed you the free vibration equations given the system's undamped, underdamped, critically damped, overdamped. We showed you all the math behind those equations. And then we showed you how to apply initial conditions to a vibration problem. All right. This week we're going to look at the topic of forced vibration. So remember free vibration last week, there was no external forcing function acting on the system. With forced vibration problems there is. Now the most common type of forcing function you'll see is a sinusoidal forcing function in the form F0 sine omega t. But forcing functions aren't limited to being sinusoidal. You can have pretty much any forcing function, a constant force, an exponential force, whatever you want. Now to analyze any vibration system, remember from last week we want to draw a free body diagram of the system. Now this is the free body diagram I stole from the textbook and it's slightly incomplete. Right. Their free body diagram is labelled forces in the x direction but not in the y direction. So just note that there'll be a weight force acting down and a normal force acting up, obviously. Now, we know equilibrium is maintained in the y direction, so there's no need for us to do any calculations there. What we're interested in is the behavior in the x direction. So we've drawn our free body diagram, and then we apply Newton's second law in the x direction. And then from that, we get our equation of motion. Right? We stepped this process out a little bit more last week. This week, you'll see we get the exact same left-hand side. We get a second order ODE, x double dot plus c on m x dot plus k on mx. Last week, the right-hand side was 0 for our unforced problem. Right, now that we're dealing with force vibration, there is a function on the right-hand side, whatever the forcing function is. So in our case, our forcing function is F0 sine omega t, and we've divided everything by m to put it in standard form. So that's why there's a divided by m on the right-hand side. Now, as with last week, we prefer to describe that second order ODE in terms of natural frequency and damping ratio. Remembering that natural frequency is the square root of k on m, and your damping ratio is c over 2m omega n. So making those replacements, the ODE looks like this. X double dot plus 2z omega n x dot plus omega n squared equals your forcing function divided by m. And then we have to ask ourselves the question, all right, well, we've modeled this system as a second order ODE, and this time it's a non-homogeneous ODE. The right-hand side is not 0. So the question begs, how do we solve this type of ODE, this mathematical problem? Well, whenever you solve a non-homogeneous ODE, the solution has two components. It has the homogeneous component, xh, and then what we call a particular component, xp. Now, the homogeneous component is the solution to the ODE, where you just pretend the right-hand side is 0. Right? And we covered how to do that last week. We covered the full mathematics behind that and the final equations we end up with. And remember what I said last week? You don't have to derive those equations every time you solve. You can use those equations now that we've derived them in general terms. Right? So xh is just going to be one of the 4 equations we derived from last week, depending on whether the system's underdamped, overdamped, critically damped, or undamped. Right? Just pick the correct equation. But how do we get this xp, this particular component of the solution? Well, to get the particular component of the solution of a non-homogeneous ODE, what we do is we guess or we assume the general form of the particular solution based on what the right-hand side of the ODE looks like. So you can see in our case, the right-hand side of the ODE is a sinusoidal function. So we're going to assume that the particular solution is also a sinusoidal function, right? But we describe that sinusoidal function in general terms, meaning we don't know what its amplitude is, capital X. We don't know what its phase shift is, phi, right? We do know, however, that our guess for the sinusoidal function has to have the same frequency as the right-hand side. So see how in our guess we've put a capital omega there, which is the same as the frequency we said the forcing function acted at. Now, if you go through the math, substituting that into the ODE and solving for amplitude and phase, you get these answers. All right? This is our equation for amplitude. This is our equation for phase. So what does Dave want to do as your math lecturer? He wants to show you how that works, how we get there. Now, in this unit, I believe a sinusoidal forcing function is the only type of forcing function you have to deal with. All right? So once we've shown you where these equations come from for amplitude and phase, you can use them in the unit. But just keep in mind, as I said earlier, within this unit, you might only get a sinusoidal forcing function, but in life, you can get all different types of forcing functions. For the weird ones, the ones that aren't very common, you will have to go through the full mathematical procedure. You won't be able to find someone who's developed an equation for you already. So understanding the math is important to have a general understanding of forced vibration problems. Right? So, derive the particular solution for a vibration with the sinusoidal forcing function. We want to get the same answers as we saw in the previous slide. So that's the second order ODE we're trying to solve, and at the moment we're just interested in the particular component of the solution. So we need to make some sort of assumption about the general form of xp, the particular solution. Because the right-hand side's this sinusoidal function, we assume xp is also a sinusoidal function. Now, in its final form, we like to have a single sine function with a phase shift, right? But when we're mathematically molding this equation, it's going to be a bit easier to deal with it as a cos component plus a sine component. So let's say for now xp is a cos omega t plus b sine omega t. We know at the end of the problem we can convert that into a single sine function with a phase shift. Now I want to sub xp into my ODE everywhere I see an x, all right? And I believe I'm missing an x right here. So where the x appears, I substitute xp, right? Where x dot appears, I want to replace that with xp dot. And then where x double dot appears, I want to replace that with xp double dot. So I want to quickly evaluate what the first and second order time derivatives of xp look like. We'll have to use the chain rule since we've got a linear function inside of a trig function. So that's our xp dot term right there. I've just derived xp with respect to time using the chain rule. And then we want to derive that once more to get the second order derivative of xp. And once we've got those terms, we can substitute them into our ODE. So we get this giant-looking expression here, subbing in our guess for the particular solution. Now you'll notice that there are two unknowns we want to try and solve in this problem. We want to try and solve the unknown coefficients, A and B, of our particular solution. So because there are two unknowns in the problem, we need some way of developing two equations. Because we know if we have a system of two equations, two unknowns, we can generally solve that problem, right? So currently it appears as though we only have one equation. How do we turn that into two equations? Right? Yep. Yeah. Yeah, exactly. Sine and cos are linearly independent functions. So I can develop one equation that only contains the cos coefficients, and I can develop a second equation that only contains the sine coefficients. Right? So we'll go ahead and do that. Firstly, I'm just going to look at all of the cos coefficients on the left and right hand side of the equation and say they're the same. So looking at the cos coefficients, we've got omega n squared A minus omega squared A. So we've got that many cos terms. Plus, there's a 2 zeta omega n omega b cos term as well. Those are all of the cos terms I can find on the left-hand side. Everything else is a sine term. And then how many cos terms are there on the right-hand side of the equation? There are none. There is not a cos term. That's equal to 0.
Sorry, what about the very first one being the negative omega squared A cos pi?
I've got that here. I've grouped both of those into the one because they both have a common term of A. So yeah, there are 3 cos terms. 2 of them have been grouped together because they both had an A as a part of them. Right? We can do the same thing with the sine terms now. I want to list this in the same sort of order. So firstly listing all the A terms and then the B terms, just so it's nice and straightforward to solve the system later on. So looking at the sine coefficients with an A in them, there's just this one here, negative 2 zeta omega n omega A. And then looking at all the sign coefficients that have a b in them, there's this omega n squared b, which is positive, and then there's this capital omega squared b, which is negative. All right. So those are all the coefficients of the sign terms on the left-hand side. And then if we look at the coefficients of the sign terms on the right-hand side, there's just one sign term with a coefficient of f naught on m. Sorry, I don't know why I divided by 2. F naught on m. So see what we've developed here, right? A system of two equations with two unknowns. Call that equation 1, and equation 2 if we want. At this point, we just want to solve for a and b using some sort of algebra or linear algebra. And for this particular problem, I decided to use Cramer's rule to solve. You can pick whatever method you want. All right, this is a linear system of equations, so you can solve algebraically, you can use row operations, do whatever you want, really. Is there anyone here who hasn't heard of Cramer's rule? Fun fact, the guy of Seinfeld invented it. All right, no one's put their hand up, so I'll just assume you know what Cramer's rule is. But I'll explain what it is as I go. Right? So if I want to solve the coefficient A, I take the coefficient matrix for the system, but I replace the column that A appears in, so the first column, with the right-hand side. All right, and every other column in the matrix stays the same. I take the determinant of that matrix, and then I divide that by the determinant of the coefficient matrix. So element 1, 2, 3, 4. All right. All right, is that making sense to everybody? How I've applied Cramer's rule? I've got the determinant of one matrix over the other. The bottom matrix is just the coefficient matrix for this system of equations. And the top matrix is the coefficient matrix, but with the first column replaced by the right-hand side. Cramer's rule is not normally a great method to use, but in this case it gives us a really nice looking answer, which is why I'm using it. So we need to solve the determinant of 2 by 2 systems. Remember, we do that through AD minus BC. Right? So the determinant of this numerator matrix is 0 minus BC. And then we get the determinant of the denominator, AD minus BC. So that's what the coefficient A looks like, the coefficient of the cos term. And then we can do a similar thing to evaluate the coefficient of the sine term, B. Now, because I want to solve b, the variable that's in column 2, I replace column 2 with the right-hand side on this numerator. Right, so the numerator looks a little bit different when I'm solving for b. We still divide by the coefficient matrix though, so the denominator is the same. So we then solve the determinants of those matrices through the formula AD minus BC. And that's B. That's the coefficient of the sine term in the particular solution. So if I describe my particular solution as A cos omega t plus B sine omega t, those would be the coefficients I use for A and B. Those would be the equations, right? Now it turns out in vibrations, we typically prefer to describe a sinusoidal function in terms of an amplitude and a phase shift rather than a cos and a sine component, right? So we now want to convert this into amplitude and phase. Remember, we can get x, the amplitude of this sine function, through Pythagoras' theorem. Square root of a squared plus b squared. Now note there's a common factor in a and b. Right? They both have an f0 on m on the numerator, and they both have the same denominator. So I can bring that outside of Pythagoras' theorem. Because all I'd be doing is squaring them and square rooting them, so they don't change at all. And what's remaining once I've factorized those common terms? Well, in B, I still have the omega n squared minus capital omega squared. And in A, I've still got the 2 zeta omega n capital omega. So that's what I get when I apply Pythagoras' theorem. And what you should see is that this equation here is just the square root of the denominator. Right? Everything under the square root is the same as the denominator. So we can simplify that. All right? X to the half over x is x to the minus a half. I just put a square root on the denominator. So that's what x looks like, the amplitude of the sine function with a phase shift. that forms the particular solution of the problem. Now you'll notice that this equation looks slightly different to the one I presented on the slides earlier. On the slides, what they like to do, and what they like to do in textbooks, in your lecture, all that sort of stuff, instead of having mass in this equation, they like to have the spring constant, K, in the equation instead. So you might recall that omega n is the square root of K on M. So I can replace M with K over omega, the square root, yeah, K over omega n squared, all right? So I'll need to replace the M here with K on omega n squared in order for the equation to match those from your lecture slides and from textbooks. So we end up with that there, which should have been what was on the lecture slides before I started my working. So what this substitution does is it gives us these capital omega over omega n ratios in our equation for amplitude. All right. I think that's known as the magnification ratio or something like that. But it's basically indicating how close the frequency of the forcing function is to the natural frequency. What we want to avoid is that ratio equaling 1. Right, if that ratio equals 1, the forcing frequency is the same as the natural frequency, and things do not go very well. We get resonant problems that vibrate with very large amplitudes. Anyway, that's the formula for the amplitude of the particular solution. Now, if we want to solve phase, we want to take the arctan of the cos coefficient divided by the sine coefficient. So the arctan of A on B. Remembering, up here, that's what A and B were solved to equal. So if we do that, the common factor of F naught on M divided by denominator, those terms all cancel, right? So what you're left with is the negative 2 zeta omega n capital omega divided by the omega n squared minus capital omega squared. All the common terms will cancel once you divide. And then once again in textbooks, in your main lecture, they'll prefer to have this ratio in the final equation, the forcing frequency divided by the natural frequency. So if we want to convert to that form, I'm just dividing numerator and denominator by omega n squared. So if we do the same thing to the numerator and the denominator, assuming it's a multiplication or a division, right, we still have an equivalent ratio. I can divide both sides by omega n squared. And that's your equation for the phase. So whenever you have these forced vibration problems with sinusoidal forcing functions, you know the particular solution will have an amplitude of x and a phase of phi, which are given by these equations. You can use those equations when you get a forced vibration problem, but if there were any other forcing function, you'd have to go through the full mathematical procedure to get an answer.
I'm a little bit confused about the relation of m to k or omega n squared.
Yes.
How did you get the omega n squared inside the square root?
Where? In?
Yes, from that upper step.
From here. How do I get it in here?
Yes.
Right. So, basically what I'm doing is I'm dividing this denominator by omega n squared.
Okay.
Right? And you can think of the square root and the square as cancelling each other out. So if I divide the front of this by omega n squared, I can divide things inside the brackets by omega n squared as well.
Okay.
Does that make sense? No? Why not?
So k or omega n squared, you would be dividing that omega n squared with.
So I just replaced the n with a k, right?
Yes.
And then this denominator, I want to divide by omega n squared.
Yes.
Okay? So if I want to divide this denominator by omega n squared, right, instead of having it outside of the square root, let's say I put it inside of these brackets. Okay? Once I put it inside the square brackets, right, instead of dividing by omega n squared, I'm dividing by omega n to the 4. But then when I put it inside the square brackets, it turns back into a 1 divided by omega n squared. So I'm just dividing everything in the brackets by omega n squared is all I'm doing to change the denominator. Right? Okay. So now we know what the particular solution looks like for a forced vibration problem. Now, I just want to piece together the full solution process you'd apply to solve vibration problems in this unit. All right? So we're throwing the deriving of formulas, the pure math out of the way, and now I just want to concentrate on what you would do in an exam scenario or for an assignment. Right? So whenever we have a forced vibration problem that needs to be solved, step 1, we want to draw a free body diagram and generate an equation of motion. Step 2, we want to solve what the natural frequency of the system is and what the damping ratio of the system is. Step 3, we write down the general solution to the ODE, which is the free vibration solution, which we saw last week. All right? Note that your damping ratio from part 2 will indicate what equation you're meant to use for the free vibration problem. Right? Zeta will tell you whether it's undamped, underdamped, critically damped, or overdamped. Step 4, write down the particular solution, the equation we just derived. Right? You don't have to model it from scratch, just use the equation. Step 5, the total general solution. is the homogeneous component plus the particular component. And then part 6, apply initial conditions to solve unknown coefficients. All right, that's the general procedure you'll want to use to solve forced vibration problems in this unit. If it's a free vibration problem instead, just cut out step 4 and 5. Right? The other steps remain for a free vibration problem. So now that we've got an idea of the process or the algorithm we'd apply to solve a vibration problem, we'll go through and solve an example. We want to solve x for the following problem, and we're given these parameter values. We're told what mass is, what the damping coefficient is, what the spring constant is. We know the magnitude of the forcing function, the frequency of the forcing function, and we're given 2 initial conditions. Right? Everything we need to solve a forced vibration problem. So, what was step 1 when we're solving this problem? Draw a free body diagram and get an equation of motion. Oh, God, stop doing that. Okay. So a free body diagram, we've already seen on, I think, the second slide to this lecture. What sides were these connected to? So that's what our free body diagram looks like. We've got this forcing function acting in the positive x direction. The spring and damping forces act in the negative x direction. And then in the y direction, we've got these mg and normal force terms that will cancel each other out. So then we apply sum of forces in the x equals mx double dot. And this will leave us with our second order non-homogeneous ODE we saw at the start of the lecture. Right? Now you'll always get this equation if the problem has a single spring, a single damper in it, right? The reason I show you this full process is so that you can solve problems that have multiple springs, multiple dampers. And eventually, if you do more vibration content, multiple masses as well. It's very important you understand how to draw the correct free body diagram to get the equation of motion. Now we're given parameter values. Right? So we could sub numbers in at this stage if we wanted to, sub in the value of m, c, k, f naught, and omega. In this case, m is 1, so there was no need for me to divide by m. It's already in standard form. But normally you would want to divide by m. Okay? In any case, it's not 1. You would want to. So that's our equation of motion, having the parameters all substituted in. Now, step 2 says to solve the damping ratio and the natural frequency for that problem. So remember, natural frequency is just the square root of k and m. Which in this case is 10. The k value is 100, our mass is 1. And then our damping ratio is c over 2m omega n. When we solve that, we get 0.5. Now, whenever you solve the damping ratio, you need to think to yourself what type of damping occurs in this problem. Undamped, underdamped, overdamped, critically damped. Well, in this case, our damping ratio lies somewhere between 0 and 1, so we'll have underdamped vibration. Okay? This is important to identify because then in the next step, when we write down the homogeneous solution or the free vibration solution, we need to select the correct equation. We need to, in this case, select the underdamped free vibration solution. So we're getting the homogeneous solution by applying the free vibration equation from last week for underdamped vibration. Let's check my notes to remember what that looks like. So that's the general solution for free vibration we got last week if the system's underdamped. You could describe this as a single sine function with a phase shift, right? Or as a cos plus a sine. Just write that down. Yeah, it should be on your formula sheet for an assignment. You can write that down. Just say it was in the lecture slides. Right, we already know what zeta and omega n are. It's pretty easy for us to work out omega d, so we can sub the values in. Looks like that. Step 4. We need to get the particular solution. We're just using the equations we've just derived. Our equation for x, the amplitude of our particular solution, and then phi, the equation for the phase of our particular solution. So that was the equation we got for x. It's a pretty long one. You substitute all your parameter values in for this problem, you get 0.1387. And then our phase, this is arctan function. And you have to be a bit careful whenever you have an arctan function. Right? Tan is positive in 2 quadrants and tan is negative in 2 quadrants. Your calculator only gives you the answer from one of the quadrants, right? Now, in this case, all right, you can see the overall value inside the brackets will be a positive number. All right? Tan is positive in quadrant 1 and quadrant 3. Your calculator will give you the quadrant 1 answer. But do we want the quadrant 1 answer? No. We've got a negative x component and a negative y component. We want the third quadrant answer. Does that make sense how we've established the quadrant the answer needs to be in? Negative x and negative y components. So your calculator is going to return a solution of 0.5880. But that's a first quadrant angle. Right? That's in between 0 and pi on 2. That number. So to make sure it's in the third quadrant instead, we have to add pi radians, or 180 degrees to it. And so with that, the particular solution has been solved. That's what the particular solution looks like. So now that we've got both the homogeneous solution and the particular solution, step 5 is to add the 2 solutions together. And then step 6 is to apply your initial conditions. Unfortunately, we've run out of time to finish those steps off, but we'll complete them at the start of next week's lecture, and in the meantime, you can look up the answers on Blackboard if you want to see the full solution. All right. We will have time to fit it into next week. Well, it'll be in 3 weeks' time, right? But the next lecture we have, we'll have time to finish this problem off. The math we cover in the next lecture is fairly simple, but very important. You'll be using it a lot, but it's very simple.